People are still coming, but maybe it's about time. Okay, let's start this afternoon's session. So the first talk is given by Joao Penedones. I probably pronounced the name wrong, sorry.
Nice.
Okay, he will be telling us about S-matrix bootstrap for effective field series. Okay, let's welcome.
Thank you. Thank you very much for this invitation. It's really a pleasure to participate in such an international conference, as I was just saying. Yes, so today I want to tell you about this program that we've been working on already for a few years on developing, if you want, a new approach, if you want to revive this old idea of the S-matrix bootstrap, essentially by taking a numerical approach to it to try to come up with a systematic algorithm to implement this idea. Okay. So today I'm going to tell you, well, my goal is a bit too ambitious, but let's see how it goes. I want to tell you about how this idea works when you're dealing with effective field theories that describe the low energy interactions of massless particles. And since I don't have much time, I will focus on this example of supergravity, but really the idea is more general, so the methods are more general, and you can see here other references for other systems. Okay, so just a very brief introduction. So as I said, we're trying to develop this bootstrap approach. And myself, I come from the conformal bootstrap background. So there, really, it was a very successful story that just by imposing consistency conditions on conformal field theories, we can really nail down and, I don't know, for example, obtain the critical exponents of Ising model with high precision. Okay. So our idea was to say, well, what about massive quantum field theory? Can we devise a similar strategy? And of course, we went back to the idea of the S-matrix bootstrap, and we tried to combine with these numerical methods to make algorithms that would really extract the maximum of all the constraints of the principles of the S-matrix, like Lorentz invariance, unitarity, causality, etc. Okay, so it's an old idea, but this systematic or numerical approach is perhaps our novel twist. Okay, and today, as I said, I'm going to focus in effective field theories. Well, you could be in the context of quantum field theory at the end of some RG flow where you have Goldstone bosons and you have some effective field theory describing their interactions. Or in the case I will discuss in more detail, will just be gravity. So we don't know what the UV is. Could be string theory, could be something else. But we have some effective field theory for gravitons, which is just GR plus some higher derivative corrections. And in particular, I will be discussing supergravity just for simplicity. Okay, so to avoid to deal with so many tensor structures, supersymmetry will help me. And so I will discuss this algorithm in this context of the example, because I think it's good enough. But as I said, probably the most important message for you is that there is an algorithm that can be applied to basically every effective field theory. And well, it's still under development, but there's already a basic algorithm that works and it's being improved. Okay, I probably will not have time to discuss pions. Okay, so I will start now with describing the problem in supergravity very quickly so that we have a concrete problem in mind, and then I will explain the method. Yeah, I forgot to say, but please interrupt me if you have questions. I probably won't have time to say everything, but it's still better if you ask me questions than if I finish and it's total silence, okay? So interrupt me at any time if something is not clear. Okay, so we're gonna focus on maximal supergravity d equals 10, okay? Maximal supersymmetry is just a trick so that we have simpler amplitude. So in particular, I will focus on the 2-to-2 scattering of gravitons, or in fact, the full supergraviton multiplet. And what supersymmetry buys us is that the full amplitude for all particles in the multiplet is given by some prefactor that contains all the polarization structures times a single function of the Mandelstam invariance STU, okay, which sum to 0 because they're massless particles. Okay, so the function we want to study is that single function, so it's like a scalar scattering amplitude. And we know several things about this function. So we know that at low energies, this is fixed by supergravity. And for example, there's one component in this function which just corresponds to multiplying a by s to the 4, which I will call t. So we'll focus on that. So t is just a scattering amplitude of two massive scalars, say in type 2b supergravity, for example, two complex scalars. And so at leading order, it has these two diagrams that are given here, T channel and the U channel graviton exchange, okay? And we shall see that basically unitarity for T as a scalar amplitude is the same as unitarity for the full supermultiplet. So that's why we focus on T. However, if you go up, so actually let me show you already. So this is the first term, this is equal to this, it's just a different way of writing it. If you continue now in the low energy expansion, the first thing that is allowed is a constant in this expansion, which corresponds to an R to the 4 correction in the effective field theory, okay? So this is, well, I could explain you this, but I don't have time. So take it just as the property of supersymmetry. Because of maximal supersymmetry, the first higher derivative correction that you can add on top of supergravity of the two derivative action is a R to the 4 term, okay? So you jump to from 2 to 8 derivatives, okay? Okay, so our target, just as a toy model, is this Wilson coefficient. Okay? So it appears here in this coefficient, but I define it precisely by the coefficient in the amplitude measured in units of the Planck length. So that's our target. Which values of alpha are compatible with the principles of causality, unitarity, and Lorentz invariance of the scattering amplitude. Okay, so before we actually develop the machine, let me tell you what is known about this in theories where we know UV completions. So take superstrings and compute this alpha. So you have two superstrings, both are maximal supersymmetric in 10 dimensions, type B and type A. And in those cases, alpha, we know it exactly, okay? So it's given by some Eisenstein series, some function of the string coupling, or in type 2A is really some elementary function of the string coupling. And if you plot these functions, you see that these functions take values when you vary the string coupling over all the allowed space. These functions take values from basically 0.14 to infinity. Okay, so you see here, there's a minimum, then they take all possible values, and same here. Well, the values are slightly different, but they are, to our numerical precision, they are both 0.14. Okay. Okay, so that's one thing. We know that from 0.14 to infinity, we should not be able to exclude the theory because we know examples, superstring theory. Okay, and another thing we know is that we can write a dispersion formula for alpha, which is very simple, which shows that alpha is positive. Okay, so in terms of this T amplitude, this scattering amplitude of charged scalars, is just some integral over the imaginary part, over the total cross-section of these charged scalars. And well, this is the usual contour argument that probably maybe Andrew will review partially in his talk afterwards, but let me not go into that. So it's simple to derive this formula, which shows that alpha must be positive, okay? So therefore, the status, before we start the numerics, this is what we know. We know that alpha is some real number, that for sure it's possible if we take it bigger than 0.14, because we know theories that realize that. It's impossible to be negative because of the sum rule. And then there is some small gap between 0 and 0.14, which we don't know. Can it be realized or not? Are there UV completions of supergravity that realize alpha between 0 and 0.14? So if you want, this is the non-trivial question, which you can call you can think of it as a swampland question, if there is a UV completion for this effective field theory. Okay. So is the problem clear? So this is, I think, all I have to say about the problem. It's a good time to ask a question if the problem is not clear. Okay. So this is just the example to have in mind. Now let's discuss something more general. Let's see how to actually apply this algorithm, the numerical S matrix bootstrap, to answer this question. So the algorithm has basically 3 parts. Okay. So first step, we do something exactly. So we just write an ansatz for the amplitude that satisfies all these properties exactly. Okay, so it's Lorentz invariance, it's crossing symmetric, is analytic in the sense that it is maximally analytic. Okay, so the only non-analyticities are the branch cuts associated with production thresholds. Okay, so what's sometimes called Mandelstam analyticity. And we also impose that this ansatz matches the low energy predictions from the effective field theory. Okay, but this ansatz has a lot of free parameters, so it encodes a very big space of possible S matrices that satisfy these properties. So this we can do exactly. I will explain. Then step number 2 is where, step number 2 is a matter of writing the unitarity constraints. So to do this systematically, we project into partial waves of a given spin, and we just impose that each partial wave must obey unitarity for all spins and all energies, all center of mass energies. Okay, so that we write the constraints, but we are not able to solve them. So then we take this large set of constraints, if in principle infinite set of constraints, and we give it to an optimization algorithm, and we just do a minimization problem with under these constraints. Okay, so that's, in our case, we're going to minimize alpha, right, this parameter. So let me just qualify a bit this algorithm. So there is one more thing that I should emphasize. So the ansatz will have a number of parameters that will be labeled by n. So this capital N, you should keep in mind, it counts the freedom we put in our ansatz. Okay, so we want to send n to infinity to have arbitrary freedom to cover all possible S matrices. And then another thing we're going to do is that because the computer cannot deal with infinite number of constraints, we're going to only input constraints up to a maximal spin, capital L. But again, this is a cutoff that we want to send to infinity. So in fact, the last step, we need to extrapolate both these numbers to infinity so that we have an exploration of the full spate of S matrices and imposing the full set of constraints. Okay, so that's why the numerics becomes a bit heavier. It's basically because we have to extrapolate these 2 parameters to infinity. Okay, so this is the algorithm. Now let me explain you a bit in more detail how each step goes. So first step, let's not look at the formula too much. So first step, the most important part is this picture down here. So what we do, we have a function of S, T, and U. And as a function of S, the analyticity is given by the plane. So you have the full analytic function in the complex S plane minus the cut from 0 to infinity, which corresponds to the production thresholds. So what we do is we think of the function as a function of 3 independent variables of S, T, and U, where in each variable we have this analyticity, full complex plane minus the cut. And then how do we write functions with this analyticity? Well, we use a very simple trick. Just take the cut plane and map it to the unit disk. Okay, so well, I even wrote here the formula. This formula works. It takes this cut plane and maps it to the unit disk in this row variable. So now you have three row variables, row of S, row of T, row of U, and you just write, you have a function which is analytic in the product of three disks. So you just write a Taylor series. You see, the Taylor series will converge inside the disk because the function is analytic inside the disk. So that's what we write here, a triple Taylor series. So this is this part here. And crossing symmetry is trivial to impose. You just put coefficients which are symmetric in the powers ABC because you want permutation symmetry between ST and U. Okay? So that's the basic idea. And of course, then when you want to measure the amplitude, you consider this amplitude in the manifold S plus T plus U equals 0. Okay? So you have, if you want, an extension of the function, but then the only physical part is the part S plus T plus U equals 0. Okay, that's the basic idea. Then here for supergravity, because we had these poles coming from supergravity, we add them by hand. And this term is basically to control the growth at infinity. So these are kind of more detailed things specific to supergravity. I can explain, but let me not do it now in view of time. Okay, so the main point is that we just write Taylor series in these conformal mappings of the cut planes. That was the main idea. Okay, so that's it. That solves analyticity and crossing. And you see n appears as the truncation in this polynomial, in this Taylor series. If you want. Okay, point number 2. Well, here at the top, there is some explanation why this is true, why unitarity of the full amplitude is equivalent to unitarity of this charged scalar amplitude T. But let me not go into that. That's just a technicality. So in practice, what we do, we take the scalar amplitude T and we compute the partial waves, okay, SL. So these SLs are the probability amplitudes to go from a state with n total energy square root of S and spin L to the same two particle states. And therefore, the square is a probability and has to be less than 1. So unitarity is just this quadratic constraint for all spins, which again we truncate at some capital L, and for all S's from 0 to infinity, for all energies, which we basically put some dense grid. But this is actually easier to extrapolate, so we do several grids and we are quite sure that nothing is changing. So numerically, we see nothing is changing with the density of this grid. Okay, so unitarity, the important point is that these partial amplitudes, they are linear in T. So they are linear in our parameters that appear in the T, in the parameterization in T is a polynomial in row variables. And then the constraint is quadratic. Okay, so we have quadratic constraints on your parameter. So when you have problems of this type with quadratic constraints, and moreover, they are convex because there's like something inside a circle, it's a problem, it's an optimization problem of the type of semi-definite programming. Okay, so there are very efficient algorithms. And in fact, we use the code developed by David Simons-Duffin for the conformal bootstrap, this SDPB code that, so we use it to solve this problem. So what we do now is to minimize alpha in the problem we have at hand for each n, so for a fixed number of parameters, and for a fixed L for every number of constraints. Okay. And that's the result. Okay. So the result is shown here. So this plot is important that you understand. Otherwise, I think you're wasting your time. So n measures how many parameters we put. So if we increase n, we are able to make alpha smaller. Okay, so we're minimizing alpha. If we have more freedom in our ansatz, we are able to make alpha slightly smaller. On the other hand, L is the number of constraints. So as you increase the constraints, it's harder to make alpha minimum. So you see the curves grow with L and decrease with N. And as I said, what we want to is to extrapolate. So we want to see to go to L equals infinity. So that's easy because you see that there is this plateau. So L equals infinity. Well, I think here around 200, basically it's infinity, but still we extrapolate carefully by fitting with inverse powers of L. So this is what I'm showing you here. So for each fixed value of N, I extrapolated to L equals infinity. And these points here, maybe I'll do like this. You see this point here has some error because we estimate the error by extrapolating with different power laws by choosing subsets of points. So we have some error in the points that we extrapolated. And then we extrapolate again to N equals infinity. Okay, so we extrapolate twice. But the remarkable thing is that once you extrapolate twice, the result you get, the final result you get is written here, is that the minimum value with these two extrapolations that we can obtain is actually very much compatible with the 0.14 realized in string theory. Okay, so this was to some extent a surprise, was not put by hand. So let me summarize here the results of this exercise. So we had string theory realized 0.14 to infinity. We had an analytic argument that excluded negative values. And now we have a full numerical algorithm that imposes all constraints on 2-to-2 scattering in a systematic way. And well, it's a difficult numerical problem. I mean, it was really difficult to make it converge. Actually, it was not my collaborator, Andrea Guerrieri's ingenuity and perseverance to make this numerics work, we would not get it. But you see that, well, I think it's quite convincing that this is indeed approaching a number which is very close to the 0.14. So it seems that this gap between 0 and 0.14 is really forbidden by basic principles. Okay? Of course, it's very important that we improve our numerics because we'll still have a big error. So it's a non-trivial question to make sure that this number is exactly the number of predicted by string theory. Okay, any question about this? So this was one example, main method, and the result you got. Okay, so how much time do I have left?
7 minutes, more than 8 or 9 minutes. Can you hear me?
Yes. Okay. So I thought I had 25 plus 5 of questions, but you're giving me all the time.
You can.
Okay.
Including questions, yeah.
Including questions. Okay. So yeah. So let me see. Okay, I'll just show you the picture. Okay. So for pions. Okay, this slide is a bit dense. I thought I would not have time, but for pions, you can do the same. You can do pi-pi scattering. And basically there's two, I mean, the leading, so this is the effect, the chiral Lagrangian. So there's two, let me mark them like this. There's two Wilson coefficients or low energy constants for the SU2 chiral Lagrangian, two leading ones, and they appear here and here. Okay, so I call them alpha and beta because you require some choice of scheme. So here I fix the scheme by fixing the logs, by fixing the argument of the logs here at the one loop. So alpha and beta are a specific choice of scheme for these parameters. And then you can ask again, what are the allowed values of alpha and beta? And we just run exactly the same type of algorithm that I just explained you, and we got this picture. Okay, so now it's a two-dimensional plane. It's two parameters, and the allowed region is this green region. Of course, you see that there is still some, this is as n is increasing, we're still growing the allowed region, but it's converging almost everywhere. Perhaps here at the central part, we still need to extrapolate a bit more carefully. Okay, but this is just another example of an application of this method. Okay, so in view of time, let me conclude. Yeah, I think this is an important point. So this method is what's called a primal method because we actually construct a solution. There's other methods which are often called dual. So primal and dual is a technical term in optimization theory. And dual is the opposite. So you see, when you increase your numerical precision in the dual method, you exclude more. While in the primal, when you increase our numerical precision, we include more. So when you have both, then it's ideal because then you can just approach the optimal bound from both sides. So there was a very recent paper about this in 4 dimensions for massive particles. So hopefully we will generalize it to massless particles. That will be very important. And of course, there is a huge amount of work, including Andrew's work that he will explain in his talk after me, about what I would also call dual methods. They're basically analytic methods to exclude theories. However, there's a bit of a difference because so far these methods basically only use the linear part of unitarity. Okay, so we're using the full nonlinear unitarity. If you want to write it in terms of FL, would be imaginary part bigger than the modulus square, while most of these works only use positivity. So at the moment, it's unclear like how much constraining power, how much more constraining power you get by doing the full nonlinear, but it would be good to understand that. And okay, I should probably stop. Yeah, there's a lot of things to do about gravity and about quantum field theory. We have some ideas to input UV information, not just do this bootstrap blindly, but also with constraints from what we know about the UV theory. But probably it's better if you ask me about it if you're interested. Okay. Thank you very much.
So any questions from the room? Any questions online? Maybe I can try that first. No.
Hello, Joe. I have a question. Sure. On your slide of your final result, you know, the N is a string theory. Yeah, this one. Yeah. I have a question. Now, what's the equivalent, you know, number of freedom, you know, parameters N for the string theory? Well, let me phrase them. Yes, please.
Perhaps, sorry, do I understand your question that you mean if I take the string theory amplitude as an exact amplitude?
Yeah.
What is and then I try to write it in my basis of functions, how many parameters will I need? Is that
right. Because naively stare at the picture, right? The N is going, you know, with larger than N, you know, the white, you know, line is going down, right? But string theory is pretty low. So like, you know, I'm wondering like what does that mean?
Yes. So you see, as N, if you want, there was this Taylor series interpretation, right? So the string theory is some non-trivial function, so it will basically have all coefficients. So it will be N equals infinity. But of course, I mean, that's not really the relevant question because we know that some functions are very well approximated by a few terms in their Taylor series, right? So the question is why here we need so many terms?
Indeed.
Yeah, and that's a very good question. Yeah, we have some experience of that. So in this case, I think we don't have a good technical understanding because it's quite complex, the problem. But in some cases, for example, in the pion case, in some extremes, we know that the optimal S matrices are S matrices, for example, with a very low resonance, very light resonance. And so this is very difficult to reproduce with this row series. So because the rho series is the degree of variation of the full disk, and this light resonance is very, very close to the boundary, so it's like it's not possible. It requires very high N. So it could be a similar effect like that. That there is some kind of structure at small kind of low energy that it's hard to predict. And we have some indications. I'm not showing you here. Maybe I could show. That there are, we did see in the optimal solutions a scalar resonance and many resonances N increases. So the optimal solution has a very non-trivial analytic structure of resonances. And so this is, I think this is the main reason why it's difficult to reproduce it with a small N.
Awesome. Thank you very much. Thanks.
Yeah.
Great.
So I see another raised hand. Garcia?
Yes, this is maybe a naive question. I was wondering if you can do anything above 4 point and what kind of information you could get if you could, or what is missing when you can only cover 4 point?
Yeah, that's a very good question. Of course, yeah, we'd all like to do above 4 point, but it's just at the moment it just looks too difficult. You see, because 2-to-2 scattering as a function of two variables, like two minus time invariants. But 5 points, it's already like 5, right? I think 5 minus time invariants in there. So now to treat analytic functions of 5 variables and understanding all the cuts and all, it's really, it's not understood even the full analytic structure. So yeah, it looks really just hopeless numerically. And indeed, in the conformal bootstrap, nobody ever bootstrapped a 5-point function, which would be equivalent degree of difficulty. So in the conformal bootstrap, the idea was to go to more 4-point functions. Okay, so that was the systematic way to improve the results, to consider 4-point functions of more operators. So here we can also do that if you have more asymptotic stable particles. So we have done that in 2 dimensions, actually, multiple amplitudes, but always 2-to-2. So yeah, that's the current status. I don't know if there might be some good idea of considering some integrated amplitude, not the full 2-to-3, but some partial information, but it's open question.
Mm-hmm. Maybe another quick one. Thank you for this one. So your external state in the example you presented are always massless.
Go ahead, finish your question.
Can you also do massive external states, or is there any difference?
Yeah, massive is simpler. So we started with massive, that's easier.
Okay.
This was the most recent development to apply the same method to massless, so I emphasize that. But technically, it's actually simpler to do massive.
Why?
Well, there is a mass gap, so there's a bigger region of analyticity, and yeah, basically it's that. And also the partial waves, if you have a mass gap, partial waves decay faster with spin, so convergence with spin is also faster. I mean, even analytic, right? Frazza bound exists for massive theories, not for massless. So even theoretical analytic results are easier for massive particles. Whenever you have a mass gap, you're safer.
Thank you very much.
You're welcome. Should I unshare? I see Andrew is impatient. I'm eating up his time. Sorry, Andrew.
No, it's okay. Yeah, we can switch over.
I mean, maybe the room is frozen. I don't see the video moving. But I can hear you guys, so maybe we can go on. Yes. Thank you, Joao, again.
Thank you very much. Thank you for the question.
Can you see me? Can you see the slides?
Yes.
Okay, great.